Hello, Griffins. Video lecture number 2 for periodic table. And as always, we will explore the vocabulary we will need for the unit to get us through. What do these new science words mean? First off, ionization energy. Here is a picture of the ionization energies, the values for each of the elements in the periodic table. And notice the trend. They tend to go up as I go to the right. Hey, trends, trends, trends. Ionization energy is specifically the energy needed to remove the first valence electron from the atom. It's going to take energy from somewhere to take the electron. That is the ionization energy. Electronegativities. Here is a picture of the different electronegativities for all the different atoms on the periodic table. Cool 3D style. Electronegativity is, of course, the ability of an atom to attract another electron. I like to think about it as how bad does the atom want another electron? Some atoms want electrons, some atoms want to lose electrons. We can differentiate them like that. So an atom with a high electronegativity is going to want electrons real bad. We'll find fluorine wants it more than anybody. Atomic radius. I've heard of the word radius before from math class, and it doesn't change much in this definition. It literally describes the width of an atom, specifically the radius of the atom, measured by half of the bond length from that picture of the diatomic molecule of that element. So that's just how the scientists go about measuring it, but I want to throw that in there just in case you see it worded that way someplace, somewhere, somehow. But it basically refers to how wide is the atom? How big is it? Is it large or is it small? Okay. Ionic radius. This picture is got a ton of information in it. If we look at the left-hand side with the red, notice they're all plus ions, and the right side is all minus ions. And the red is the actual ion on the left, and the blue is the actual ion on the right. And we will see positive ions are smaller because positive ions or cations are losing electrons, where anions or negative ions, here in blue, get wider or a larger radius because they're actually gaining electrons. So an ionic radius is the radius specifically of the ion of that atom. Does it get bigger or does it get smaller in relation to the atom itself? Okay. Chemical reactivity. This picture shows us a little bit about the trends in metal and nonmetal reactivity. Chemical reactivity specifically is the behavior of an element based on its number of valence electrons and the number of shells that it has. Again, does it want to give up electrons or does it want to grab electrons? And then that's going to kind of dictate to me how it's going to react. Okay, metallic character. How metallic am I? Am I more metallic or less metallic? When we talk about metallic character, we're going to increase as I go towards the metal side. Okay, metallic character. We're going to learn what makes a metal in 2 words from now, so I don't want to tip my hand yet. But metallic character is just telling me how metallic am I? So the ability of an atom or an element to readily lose an electron, we will find that metals are losers. They readily lose electrons. They have luster, which is shine. They conduct electricity, and they can be ductile and malleable. That is the definition of a metal. So metallic character would be the measure of that. Okay. Non-metallic character is the opposite. Same picture, but now we talk about the nonmetals. So the opposite of all of those particular traits would be, whoops, too fast, the ability of the element to attract electrons. He wants to gain electrons, not lose. He'll be dull instead of shiny. He will not conduct electricity at all whatsoever. And if he's solid, he will be brittle. Otherwise, he's gas. Okay, so that's my non-metallic character. Let's be not like a metal. Okay, metals. Here's a few of them. We know most of them. We've heard of copper before, and tin, and steel, and nickel. Specifically, metals are elements that lose electrons, have luster, conduct electricity, will be ductile and malleable. And we will find, when we figure out what this staircase is, is that they all reside to the left of that staircase. It'll be a way for us to distinguish where on the periodic table the metals are. The left of the staircase is the metals. Metalloids. Metalloids are actually on the staircase, and in this particular picture, I can draw the staircase in for you. You will see that the metalloids are all touching that staircase, with the exception of aluminum. Okay, and a metalloid is just what it sounds like. It's a mixture of metallic and non-metallic properties. It doesn't have all metallic properties. It doesn't have all non-metallic properties. It has some sort of a mixture, and we'll find that they're touching that staircase. Okay, nonmetals. In this picture, it's the yellow elements are all nonmetals. Notice they are to the right of the staircase I just drew that would go through the green. To the right is nonmetal, and we include hydrogen in that mix. Hydrogen's a gas, so it's obviously not a metal. An element that attracts electrons, they're dull, they're non-conductive. If they are solid, they are brittle, and they are, of course, found to the right of said staircase. Okay, alkali metals, our first group in our definitions. We will see that this is group 1, and notice hydrogen is a different color and not labeled in this particular picture. That's because even though hydrogen is in group 1, it's not considered an alkali metal. The key word with alkali metal is, of course, the word metal, and hydrogen is obviously not that. It has some similarities, but not enough to call it in the family called alkali metals. By definition, alkali metals are all the group 1 metals. They have one valence electron, and please note, hydrogen is not a metal. It's not part of this group. It's actually floating above the periodic table, not touching. So if that's the way you remember, then that's the way you remember. Group 2, beryllium, magnesium, calcium, strontium. These are the alkaline earth metals. And alkaline earth metals are the group 2 metals. They'll have 2 valence electrons, and we remember that there's 2 words in alkaline earth, so group 2 words helps us remember which one is alkaline earth metals, because that is something you're going to need committed to memory. It doesn't tell you anywhere on that chart where they are, but you will need to know that. Same with halogens. Halogens are the group 17 metals: fluorine, chlorine, bromine, iodine, and At. I'm not even saying that name because it's just, it always gets me. I always want to say antimony, and that's not right because I always want to say it. It's astatine, isn't it? It's one of those, for whatever reason, it's my brain. I always get them mixed up, but I have a reference table. I can look them up. The part you need to know, it's the group 17 elements, and they all have 7 valence electrons. Notice I underline those 2 7s to help us remember, and they really want 1 electron. So that definition of electronegativity, how bad does an atom want electronegativity? Or I'm sorry, how bad does an atom want an electron? These are them. These are the guys that want to complete their octet or their 8 valence electrons. Okay, and if they do complete their 8 valence electrons, they will look like the noble gases. Group 18, all filled up. They got all the electrons they need in their valence shell. So noble gases are the group 18 elements. They all have 8 valence electrons, which equals a full shell. This also makes them very unreactive, very much like the nobles. They don't want to mess around with us peasants much. They stay up in their castles. All right, the only note, the exception here is helium, He, is full with only 2 valence electrons. That is because the s orbital can only hold 2, so he is full with 2 valence electrons, just like everybody else is full with 8. Okay, so he's the exception. Helium is full with just 2, so make sure we know that. Transition metals. Transition metals are the ones we skipped. They are the ones in the middle, this big old block of elements. These guys are all the transition metals. I transition from metal to non-metal in the middle, transition metals. They are also very special. They're from groups 3 to 12. They have varying properties because they aren't really they're more like an extended family, if you will. Their properties aren't definitely all the same, but they do all form colored solutions in water, which is cool. And that's one of their major properties. It's where we get a lot of the colors and all the fireworks that we see. They're all transition metals. They form cool colors. Periodic law. The law states that basically this, and I'm going to put it in other words. So I'm not going to read that all to you because you can read it. states that basically the physical and chemical properties become very predictable if I arrange them by their atomic number. Now there's a little hint about this periodic table and how it's arranged. But periodicity, the predictability, periods. Specifically, going across the periodic table is a period. And we'll see that it is labeled on the side of the periodic table to help us remember that. We just got to make sure we know how to use it to make sure we don't get it mixed up. So periods go across the periodic table. They have the same number of energy levels as it is the period that it's in. So period 2 has 2 energy levels. Period 3 has 3 energy levels. Period 4 has how many energy levels again? Yeah, you're getting the hang of that, right? Okay, on to groups. The groups are the opposite. Groups are going up and down. We will see that the periodic table is also labeled with the groups, and the colored ones are the kind of the true groups because they all have the same number of valence electrons. We'll see that we probably skipped over this BCNO group. And that's because the properties here don't really line up as much as we want, even though we have the same number of valence electrons. And that's because we're transitioning through there, the metalloids. And so we have nonmetals, we have metalloids, and we have metals. And there's really no way that those all quite react all the same way. But these are the true groups. Okay, 1, 2, 13, 14, 15, 16, 17, and 18. They go up and down. That's what we call a group. So as I go down the periodic table, I'm going to have similar properties because I have the same number of valence electrons. Like we learned when we did Lewis dots, remember valence electrons tell me how I'm going to react. Diatomic elements, these guys are all special. There's 7 of them. You need to memorize these. There's no place on the periodic table that tells us about them. They are a special group of elements that will only be found in groups of 2 in nature, like O2, N2. Okay, you'll never find oxygen as a single atom. It's too reactive. It's always bonded by itself, to itself, or it's found, and that's the element form, or it's found bonded to something else, like H2O. So I will find it not bonded to itself, but if I'm an element form, if it's going to be by itself and not bonded to anything else, it's got to be bonded to another one of its like atoms. Did I confuse you good enough? We'll go over that in class, don't worry. Make sense of it all. Allotropes. Maybe the most difficult conceptual vocab word for this unit. Here's a picture of carbon 4 different ways. Diamond, graphite, a fullerene, and soot. Basically, this big long definition sums it right up. The substances that are made up of the same element, and only that one element, but they have different physical and chemical properties because they have different arrangement in atoms. So graphite and carbon are both made of pure carbon. The graphite in your pencil you're writing with, and the diamond in your earrings you're not. But it's all just carbon. There's no other elements in there. It's just carbon, but they are arranged completely differently, which gives them completely different properties. We all know that graphite is much softer than diamond. Diamond is about one of the hardest materials we have on the planet. So there is our vocab for the unit. You guys need to study this up so you can take your vocab quiz, and that's it. See you guys in school.